And this is the main bit of what I wanted to teach today, which is electron microscopes. Okay, so there are two different sorts of electron microscopes that you need to know about. The first is the TEM, which is the transmission electron microscope. And the second is the STM, which is the scanning tunneling. 1 L or 2 L's? Oh, I think it ought to have 2. Tunneling microscope. Now, why are we using electrons to look at stuff then? And the reason is because we can accelerate electrons up to very high speeds really easily, just with the potential difference. And so long as we have the whole equipment under vacuum, well, it's not so simple, but let's assume we can. There's nothing to absorb those electrons. When they're going at high speed, they will have a nice short wavelength. The higher the speed, the shorter the wavelength. If the wavelength is short enough, then that will allow us to get more resolution than you could get from light. So visible light will allow us to go down to, I don't know, 350 nanometers. But atoms are bigger than that, smaller than that. So we have no chance of seeing atoms, individual atoms, using visible light. The wavelength is just too long. You can't resolve it. But you can basically turn the wavelength down and down and down and down by turning the voltage up and up and up and up. On an electron microscope, and improve your resolution each time. And what it means is that you can resolve much smaller things. Okay, so the transmission electron microscope was invented in 1931. Okay, so Knoll and Ruska realized that electron waves would produce much higher resolving power. That's what it's called. It's the resolving power than light waves in an optical microscope. So now, in order to do this, so this is the transmission electron microscope, you have to produce your electrons, you have to accelerate them in order to turn them into waves, and then you've got to be able to focus them, you've got to be able to manipulate them. And so there are various lenses, but these are not your regular sort of lenses. These are what's called condenser lenses. They're basically magnets. Okay, so there's a coil that goes around. Okay, so you've got a copper coil and it goes round, and it keeps coming round in front and goes round, and it keeps around it, round and round and round and round and round. Okay, so this is a cutaway view, and it is inside. Can you see? It says it's a soft iron casing. Now, soft iron will it's 5,000 times more permeable to magnetic fields than air or a vacuum. In this case, it's inside in a vacuum, and the consequence is that the magnetic field, doesn't come out of this sort of donut-shaped magnet, except where there's a gap. Can you see between those two pink in here, between there and there's a gap in the casing, and can you see that the magnetic field indicated by the dotted lines it escapes a bit, so you've got this sort of curved bit sticking out, right? So it sticks out here, and where the electrons hit the magnetic field, they get deflected. Remember that charged particles in a magnetic field of force that's at right angles to the direction of the charged particle motion and the magnetic field direction. And the consequence is that it bends the electrons that come close to the edge of the sort of tube that it's traveling down, but any that are in the middle, they don't get bent at all. Okay, so it just selects the ones near to the edge. So if I change my thing to a mouse and move this up, can you see that if you've got two electrons, okay, one that starts here and goes straight down, that one's going to get bent by the magnetic field there, and it's going to end up down there. And this one that's going down through the middle, it doesn't encounter any magnetic fields. They're too what's the word? They're too local. They're only there right at the edges, and so it doesn't get deflected at all. Now I want you to think about then this as a lens. Okay, so if this was an optical lens, imagine that we've got a lens, a thin glass lens that does this. Okay, here is my object. This is my principal axis. I've got my two rays coming from the top of my object. One comes down, comes to the middle of the lens. It's actually refracted both on the way in and on the way out, but it goes through the focal point of the lens and carries straight on. The ray that goes directly through the middle of the lens is not deflected. Okay, and where those two rays cross, that is where the image is. Oh my word! So these condenser lenses are focusing the electrons just the way that glass lenses, thin glass lenses, focus light. Yay! I know, isn't it cool? Okay, so so that's really cool, right? So now we've got a way of changing the direction of the beam, but we've also got a way of focusing the electrons. Okay, so we've got this boil them off gun. We've got accelerating voltage, and we can change the accelerating voltage so that we can change the wavelength, and we can focus our light, except it's not light, it's electron waves, and the sample is in the middle here. Okay, so and can you see that they've drawn it as an arrow facing that way, and the electrons produce an intermediate image there, and then a final image on the fluorescent screen. And in most modern microscopes now, the fluorescent screen is replaced with a CCD, and so you can collect your image and store it. Okay, so now this is where the sample that you're looking at sits, and of course the electrons actually have to go through it. It's transmitted through it. So now some of the electrons are absorbed in patches, depending on what it is that's in the way, and some will be slowed down a bit. So the electrons, they do arrive at different times, which can be a bit of a problem, and this is one of the things that can limit resolution. I mean, obviously the resolution is limited by the accelerating voltage and consequently the electron waves. It's also limited by how good you can focus your beams with your lenses. And you can see that it's really complicated. You've got a condenser lens and an objective lens and a projector lens, and it's like, oh. And in fact, in most transmission electron microscopes, everything is controlled except for very sort of high level control that a technician might have. Everything is computer controlled because it's just too difficult to optimize all these things on the fly with electrons going through a sample that's getting hot because electrons are going through it. Oh, yeah. So, yeah. But that's the basis of it. It behaves very like a light microscope, but it's electrons, okay? So there is that's the outline of the electron microscope, and this is a transmission electron microscope. Right now, I've got various, I mean, you can read this, I'm sure you can read this. This is the transmission electron microscopy, and I got various versions up. So this one is from the University of Warwick. So this is the transmission electron microscopy, and you can see they've got a similar setup. I mean, it's a slightly different arrangement in terms of the viewpoint, so you're not looking directly from the side. But you've still got a condenser lens, which is above the specimen, which is above an objective lens, which is above a projector lens. And they've got an intermediate lens and so on. They still have a fluorescent screen at the bottom of this one. Okay, and the incident beam, can you see they've got what they're trying to do is to get a parallel beam landing on the specimen. So here, this is the incident beam. Whoops, they're all coming in parallel, and there's the specimen. Okay, so, and some of the light is deflected, and you end up with a diffraction pattern too. Can you see that you end up with an intermediate diffraction pattern? Oh yes, because of course they're waves, so they get diffracted. Complicated. So so yeah, it talks about diffraction, and it talks about specimen preparation. So preparing specimens, that is a whole other ballpark, and slicing things thin enough that you can let electrons through. Oh, okay, yeah, lots and lots and lots of problems there. So if you're interested, please, I mean, electron microscopy is a whole field all on its own. This one is, I mean, it's described as nanoscience, and this is actually a manufacturer of transmission electron microscopes, and you can see that real microscopes, can you see how many lenses they've got? Okay, and this whole column, remember, the whole column has got to be evacuated. So they talk about the 5 key components: the high voltage source, because you've got to have an accelerating voltage, you've got to have a good vacuum system, you've got the microscope's column, which is all of those magnetic lenses, you've got to have detectors, so that's a camera, a spectrometer, and sometimes a fluorescent screen, and you've got to control it with the computer. So those are the 5 main parts. But this, can you see how complicated they really are? Okay, and the diagram in your notes was, it was, what was it, 10, I can't remember, 10 to 100, or was it 50 to 100 or something? 50 to 100 kV. Well, this one was 80 to, where was it? 80 to 300,000 volts. Okay, so yeah, so that you can get even shorter. And they talk about CCD. A CCD is the same thing that's in your mobile phone that detects the light when it takes photos. It's a charge coupled device. So photons land on it in the individual pixels. And they act like little buckets, and you store charge, and then the charge is read off with a sort of an array address system, and you turn how much charge is in each pixel into a black or white intensity reading, which can then be displayed on a computer screen. So yeah, that is how a charge coupled device works, yeah, if you're doing the astrophysics, you need to know about it's called the quantum efficiency of a charge coupled device, and you have to compare it to the human eye. You don't need to do that in yours, which is nice. But can you see, this is, they're trying to sell their microscopes, and the vacuum system is just horrific. There's lots of different ways of getting rid of all the gas that's in the tube. And then they talk about the gun, and can you see a thermionic emitter? And they've got various different sorts of emitters. So you only need to know about thermionic emitters. Okay, so these things get hot. Well, they've also got a field emission source. Okay, so yeah, FEG stands for field emitter gun. There you go. Film. Anyway, it doesn't matter. You don't have to know all of these different things. It's just I want you to be aware of how actually difficult this is. Okay, and it's quite interesting. They talk about the electromagnetic lenses. Okay, can you see here? It actually shows the tube as being really narrow. It really is narrow, and so the electrons, they don't get a chance to deviate much from parallel. Okay, and TEM, which is what you need to know about, is where you have a parallel beam hitting the sample. STEM, you don't need to know about. It's scanning transmission electron microscopy, I think. So in the STEM mode, the opposite is needed. So instead of having the beam parallel, it focuses it. Instead, the illumination system acts to form a convergent beam at the specimen. So, but it can do both, this one. Anyway, it's interesting because it gives you some idea about actually how real microscopes look, behave. The other one that I wanted to talk to you about, transmission electron microscope, again it's another view. I think that might be Britannica. This one. Right, now this is actually mentioned in the teaching notes. So they talk about the TEAM 0.5 and they describe it in the notes as the world's best microscope. I think it probably isn't anymore, but you can see that this was written in 2008. So that's quite a long time ago. Not quite as much as 20 years, but getting there. This one is in Berkeley, California, and the A in it means that it's been aberration corrected. So one of the problems with optical microscopes or telescopes is what's called spherical aberration. So the edges of the lens don't come to a focus in the same point, the same distance away from the lens, as light that comes nearer to the principal axis. And that's spherical aberration. And electron microscopes suffer from the same problem. Now, this particular microscope, and that's one of the things that limits the resolution of the microscope. On the whole, resolution is not limited by the wavelength of the electron waves, okay? On the whole, it's much more practical things that really limit it. So now this microscope has got aberration adjustment. It's aberration corrected. Can you see? Aberration corrected. And I mean, look at it, it's a mess. But so it's got these extra bits of magnetic fields that kind of stop it from having this aberration problem where the focal point is not the same from the edges of the lens to the middle. And the consequence is that this microscope was able to look at individual atoms for the first time. So this, they talked about this thing called a nano bridge, only a few dozen atoms wide. And that correcting spherical aberration in an electron microscope has long been possible in theory, but only recently has it become practical. So, and here, this is the Hubble. Now the Hubble, they made a mistake when they did their calculations, and when it was first put into orbit, it had a problem and they had to put glasses on it. They had to correct spherical aberration. It was very, very precisely wrong. And so they had to very, very precisely correct it. And it was the really expensive exercise putting Hubble's glasses on. But then afterwards you got much, much clearer views. You can see the difference there. Well, that was Hubble, right? Correcting the spherical aberration on this microscope, this electron microscope, meant that they were able to see individual atoms. And so, if we just, I mean, you're welcome to read this, but there are individual atoms visible. Oh, okay, so really quite scary. Okay, and this is where two gold crystals are meeting, where they're joined by a complex arrangement of atoms forming a nano bridge. So you've got one crystal of gold here, that's sort of this bit, yeah, all of this, and one crystal of gold that's here, it's all of this, and this bit, this is the nano bridge, yeah, nano bridge. Okay, and the gold atoms right now, angstroms is not an SI unit. 2.3, and angstroms is written like that with a little circle over the A, and 1 angstrom is 10 to the minus 10 meters. Okay, it's not an SI unit. They will not ask you about SI units. But the gold atoms, can you see they're 2.3 angstroms apart? Okay, and gold atoms are big. So 1 to 2 angstroms is the normal size for an atom. Okay, so okay, interesting. And they saw them for the first time, right? And the only reason they could do it was because they'd done this work, making it as the resolution as high as possible, correcting the problems with the way that the system worked. That is the transmission electron microscope, but there is one more microscope that you need to know about. Okay, so let's just scoot through this. There's that same de Broglie. The next one is the scanning tunneling microscope. Okay, now this uses quantum tunneling. So, and I think the easiest thing to do is to just show you this little bit of video because it's lovely. So we've got, can you see that those red sort of blobby things, those are atoms. A tip is brought very close to the surface and it's moved across. Now the tip is brought near, it's piezoelectric controlled. As it gets close to the top of an atom, can you see where the atoms are closer at the top where they're round? You get electrons tunneling through the gap between the tip and the atom, the electrons moving between the tip and the atom. And what it does is it turns that signal into a pattern, a grid of atoms, okay? So that is how you can find where the atoms are. This is using the tip in its constant height mode. This bit you don't need to know about microscopy, but spectroscopy of it. But if you vary the height of the tip, you can get constant current. And you can move your tip down and you can actually pick up an atom and move it and put it down. And so the smallest writing in the world has been done with one of these, and it said IBM, I think. It was really boring because it was IBM's machine that did it. But it allows you, I mean, all of this about looking at the differential of the signal, you don't need to know. It's just about the fact that this is where you can move it. Okay, so your tip gets close to an atom and you can pick it up and put it down somewhere else. Yay! So you can move one atom at a time. It's just unreal. Anyway, I just think this is glorious. So this is the scanning tunneling microscope. And there are two modes. One is, let me go back to this one. One is the constant height mode. Can you see? Constant height mode, where the changing current is used to generate an image. That was the first bit of that video. And then there's a second mode, which is constant current mode. The change of the current is used to move the probe vertically upwards or downwards, respectively, until the gap width and the current is the same as before. So you can profile the surface atom by atom. by atom. Even just between one atom and the next atom, there's a little dip, and you can get them. So so you can get individual atoms, and this is this vertical resolution of the order of 0.001 nanometers. Okay, so remember that an angstrom, and we said about 2 angstroms, right? So that was 2 times 10 to the minus 10 meters. This is about the size of 1 atom. So, I mean, it's of the order of 1 times 10 to the minus 10. Well, remember that 1 nanometer is 10 to the minus 9. So this is, so 0.1 nanometer is 10 to the minus 10. This means that that's 100 times more resolution than is needed to distinguish an atom, okay? So, okay, so it is much smaller than the size of even the smallest atom, okay? And the fun bit about it is the fact that you have to have quantum tunneling. So, in fact, there is a physical gap, and the electron has to cross that gap somehow. And it does it, there's an energy barrier there, but it does it by tunneling through. It just goes, nah, it's not there. I'm just going to go anyway. And this is the quantum tunneling bit, which is rather fun. Okay, and so yeah, it's based on quantum tunneling. In fact, respiration requires quantum tunneling too, which is kind of basic for life on Earth. So it's not as rare as you'd think it is. But anyway, light can be seen through a thin metal film because the amplitude of the light waves is not reduced to 0 by passage of the light in the film. In the same way, the amplitude of matter waves in a barrier does not become 0 if the barrier is sufficiently narrow. This process is referred to as tunneling. So there's a barrier, but the electrons, the wave, can move from one region to another through this barrier, and it's called tunneling. So so there you go. So this is the de Broglie wavelength, and this is the scanning tunneling microscope. So it's a piezoelectric transducer. So piezoelectric is you apply voltage and it changes the size of it, or if you squish it, it produces a voltage. So and that's a piezoelectric. And so you can control really, really carefully where the position of the tip is. And you can get amazing resolution, okay? So this was from 1994. Okay, it happens to be a semiconductor surface, a compound semiconductor of indium antimonide, INSB. Why would you choose that? But there you go. Anyway, right, that is the bit on microscopes, electron microscopes.